Welcome to the deep dive.
Glad to be diving in.
Today we are opening the file on, well, a single event happened just over 2 centuries ago.
Yeah, on a remote Indonesian island.
And it just absolutely rewrote the rule book. I mean, for global climate, history.
Even art, surprisingly enough.
We are plunging into the 1815 eruption of Mount Tambora.
It's a huge one.
Now, if you've heard the name, you probably think the year without a summer.
Yeah, that's the most famous connection, definitely.
But our mission today, well, it's to go way beyond that footnote. We want to understand the how.
The mechanics of it.
Exactly. How did one geological catastrophe way out on the island of Sumbawa throw enough stuff into the air to just, fundamentally force global climate systems into chaos?
And lead to humanitarian disaster across continents.
Right. It's not just volcanology. It's this terrifying lesson in how connected everything is.
And how fragile those systems can be.
Yeah.
And when you say catastrophe, we really need to stress the scale right up front. This was the most powerful volcanic eruption in recorded human history. Full stop.
Wow.
It was classified as a VEI-7 event. That's the Volcanic Explosivity Index.
Yeah.
Measures the erupted material.
Okay, VEI-7. Now, most people today, they might know Mount St. Helens in 1980.
That was a VEI-5. Significant, but much smaller.
Or maybe Pinatubo in 91. That was huge news.
Pinatubo was a big one, a VEI-6.
So St. Helens a 5, Pinatubo 6. How much bigger are we talking when we jump to a 7 like Tambora?
Well, the index is logarithmic. So each step up isn't just adding one, it's a huge leap in power.
Okay.
A VEI-7 eruption like Tambora is a full order of magnitude, so 10 times larger than a VEI-6 like Pinatubo.
10 times Pinatubo.
In terms of ejected volume, yes. The baseline for a VEI-7 is ejecting around 100 cubic kilometers of material.
That's hard to even picture.
It is. Now, when scientists get really specific, they look at something called the dense rock equivalent, or DRE. That's the volume if you compressed all the ash and pumice back into solid rock.
Okay, the actual rock missing from the mountain.
Exactly. And for Tambora, the DRE estimates are between 37 and 45 cubic kilometers.
37 to 45 cubic kilometers of solid rock. Just gone. Blasted out.
Pretty much. It was quite simply a world-altering explosion of rock and gas.
A monster. And it didn't just sneak up on the world either. It announced itself with this terrifying global sound effect.
Ah, yes. The sound waves.
That anecdote always gets me, the confusion it caused. People literally over 1,000 miles away.
Hearing these massive continuous explosions.
And thinking it was just distant cannon fire, like preparing for battle.
It's an incredible detail. The detonation sounds were clearly heard in Makassar. That's on Sulawesi, 380 kilometers away.
Okay, that's already quite far.
But the reports go much, much farther. Batavia, which is now Jakarta, that's 12,260 kilometers away.
Wow.
Ternate, 1,400 kilometers. The energy transfer through the air was just phenomenal.
And what really just hammers home the sheer energy, those documented reports from Truman in Sumatra.
Over 2,600 kilometers away.
Yeah, and people there heard what they thought were guns firing. Sir Stamford Raffles.
He documented so much of the aftermath, right? He was lieutenant governor of Java then.
He was a key source for us.
He noted in his memoir that almost everyone thought it was a naval battle or some kind of military engagement.
Raffles' observation really captures that initial misunderstanding perfectly. It was so convincing that a detachment of troops actually marched out of Jakarta because they thought a nearby post or maybe a ship was under attack.
They mistook this massive geological event for human warfare.
Completely.
And some recent analysis even suggests the rumbles might have been audible even further, like over 3,350 kilometers away. Nong Khai, Vientiane. Though those are less certain.
Still, it's possible. It just establishes the sheer magnitude. It was probably the largest sonic event of the entire 19th century.
What a way to set the stage for a disaster. A sound so vast to trick people across thousands of kilometers.
It really does. So, okay, let's look at the timeline now. What actually happened to the mountain? Okay, let's unpack this. Tambora, before 1815. It was this huge, cone-shaped stratovolcano. Looked magnificent, apparently, but dormant for centuries.
Right, and dormancy in these big volcanoes isn't exactly peaceful. It often means the magma chamber underneath is cooling, crystallizing.
And building pressure.
Precisely. As magma cools and solidifies, gases get released to get trapped, and the pressure just builds and builds relentlessly.
We're talking serious pressure here.
Extreme pressure. Estimates suggest something like 4,000 to 5,000 bars of overpressurization inside that magma chamber.
Wow.
The mountain was essentially a ticking time bomb, holding centuries of pent-up energy.
And the science started well before the big one, didn't they? Sources say 1812, it began rumbling.
Yeah, 1812. Rumblings. A small dark cloud seen near the summit. That was the first sign the structure was maybe starting to fail. The beginning of the end, you could say.
The first really big bang, though, the one that caused all that cannon fire confusion, that was April 5th, 1815.
That's right, April 5th. A massive eruption, huge pressure release, generated those thunderous sounds heard hundreds of miles away. But even that was just the warm-up act.
The main event, the one that put Tambora in the history books forever, that was April 10th. In the evening, yes, April 10th, around 7:00 p.m. local time, the eruptions just went into overdrive. Eyewitness accounts describe 3 distinct plumes of fire rising up. 3.
Yeah, and then merging into one single colossal column. Descriptions say the entire mountain seemed to turn into a flowing mass of liquid fire.
Liquid fire. Just a horrifying image. Magma, gas, superheated rock all flowing. The physical violence was just staggering. Then around 8 p.m., the sky itself started falling.
What do you mean?
Pumice stones. Rocks, often up to 20 centimeters in diameter, that's like softball size, started raining down on the surrounding area.
Whoa. Followed by heavy ashfall between 9:00 and 10:00 p.m. Imagine being there. Total darkness, deafening noise, and then massive rocks falling out of the sky.
Terrifying. And the energy was so immense it created its own localized weather.
Like a storm. More like a whirlwind. A violent whirlwind, generated by the eruption blast itself, apparently ripped through the village of Sagar, which is now Sangar.
What did it do?
Blew down nearly every house. Carried debris, even large trees, high up into the air. Just incredible power.
And the geological impact. The energy release numbers are just mind-boggling.
They really are. The estimate is equivalent to about 33 gigatons of TNT.
33 gigatons.
An almost incomprehensible force. And remember, before this, Tambora was one of the tallest peaks in the entire archipelago, around 4,300 meters high.
After April 10th.
Afterwards, the peak height was slashed by about a third, down to only 2,851 meters.
It just blew the top third of the mountain clean off.
Yeah, essentially, yes.
Yes.
The summit was obliterated, replaced by this massive hole, a caldera.
How big?
6 to 7 kilometers across, and about 600 to 700 meters deep. That caldera is the scar. It's the physical proof of where those 100 cubic kilometers or so of mountain used to be before it got turned into ash and blasted skywards.
A direct measure of that colossal volume we talked about. Hashtag tagged 1.2 local tsunami and pyroclastic flows. Of course, the destruction wasn't just falling rocks. There were these immediate secondary effects, just as deadly, moving sideways across the land and sea.
Absolutely. We have to talk about the pyroclastic flows.
These are the super hot, fast-moving currents of gas and rock.
Exactly. Scorching hot, moving incredibly fast down the slopes. They cascaded down every side of the peninsula where Tambora sits.
Wiping out everything.
Everything in their path, including the main village of Tambora itself. These flows meant total annihilation over an area of about 874 square kilometers right around the mountain.
And all that material, rock, ash, gas, rushing into the sea must have done something.
It did. It displaced a huge amount of water, generating a tsunami. Not a giant Pacific-wide one, but definitely moderate-sized and absolutely devastating locally.
When did that hit? Pretty quickly. Around 10:00 p.m. that same night, April 10th. In Sangar, the waves reached up to 4 meters high. 4 meters is significant.
It is. We also have records of smaller waves, maybe 1 to 2 meters, hitting Basuki over in East Java. And similar 2-meter waves reported way out in the Molucca Islands.
So it spread quite a bit, and the death toll from the tsunami alone.
The immediate tsunami deaths are estimated around 4,600 people, just swallowed by the sea right after the eruption climaxed. Hashtag tag 1.3, the aftermath on Sumbawa and Lombok.
The blast, the flows, the tsunami, horrifyingly fast, but then the slower tragedy unfolds on the nearby islands, Sumbawa and Lombok. The ecosystem just collapses.
Complete collapse.
Yeah.
Leading to famine and disease. The eyewitness accounts from the weeks after are just gut-wrenching.
You mentioned Alteep Phillips earlier, sent by Raffles to survey.
Yes. His report is shocking. He described finding the remains of several corpses just lying along the roadsides weeks later.
Oh, God.
Villages were almost entirely deserted, he wrote. Houses fallen down. Why? Because the survivors had dispersed in search of food.
Just scattered, trying to survive.
The environmental destruction was total. All vegetation on Sumbawa was wiped out. Gone.
And the debris wasn't just ash, right? There were these huge rafts.
Yes. Uprooted trees, all mixed up with pumice ash, washed into the sea. And they formed these immense floating rafts, some reportedly up to 5 kilometers across.
5 kilometers? That's enormous.
Huge. They were a real hazard for ships. British ships, like the Fairlie and the James Sibbald, ran into these massive pumice rafts months later, as far as 3,600 kilometers west of Tambora.
Just floating evidence of the eruption's power months later and thousands of kilometers away.
A floating monument, exactly.
Now the death toll. It's grim, but it seems complicated. The numbers vary so much in historical accounts.
They do. And that variation really speaks to the chaos of the time and just how hard it was to count victims accurately in the early 19th century, especially in a disaster zone.
It's important to separate the causes, right? Direct deaths versus indirect.
That's critical for historians. Direct fatalities, the people killed instantly by the blast, the pyroclastic flows, the initial tsunamis, that number is generally agreed to be around 10,000 to 11,000 people.
Okay, 10 to 11,000 direct deaths. But the indirect numbers, that's where it gets murky.
That's where the real controversy, or at least wide variation, comes in. Early estimates, like from a Swiss botanist named Zollinger, who visited Sumbawa later, he suggested maybe 28,000 indirect deaths from starvation and disease just on Sumbawa and Lombok.
Okay.
But then, much later, in 1949, you get this figure from a Russian scholar, Petrushevsky. He estimated an astonishing 88,000 total deaths.
88,000? That's a huge jump. How did he break that down?
He estimated 48,000 on Sumbawa and 44,000 on Lombok. So a massive number attributed to indirect causes.
So why such a huge difference? Was it just bad record keeping back then, or something else?
Seems to be a mix. Raffles himself, even though he tried to be meticulous, admitted struggling to get accurate numbers. Local governance just completely broke down.
Understandable.
Later researchers, particularly Tanguy and others in 1998, went back and really scrutinized Petrushevsky's high numbers. They concluded they were likely unfounded. Probably issues with how he extrapolated data, maybe definitions of death due to eruption.
So what's the current consensus, the number most historians accept now?
Based on reevaluating Raffles' notes, Zollinger's work, and later scientific reconstruction, the widely accepted estimate lands at about 11,000 direct deaths.
Okay.
And around 49,000 indirect deaths from the famine and disease that followed.
49,000 indirect. So bringing the total regional loss of life to
at least 71,000 people. A devastating demographic blow to that region.
71,000. Just incredible. And the specific cause of death for many who survived the initial blast? It was particularly awful.
Yes. Leighton Phillips recorded this widespread, severe, violent diarrhea in the worst-hit areas.
And they knew what caused it.
The local people attributed it, and Phillips agreed, to drinking water which has been impregnated with ashes.
The ash poisoned the water supply.
Exactly. Compounding the starvation with disease. Just layers of disaster.
So the immediate local story is just immense violence, total ecological collapse, starvation, disease. Horrifying.
Absolutely.
But as devastating as that local picture is, it almost pales in comparison to what Tambora did next, exporting its effects to the entire planet.
That's where the story goes global, and arguably even more terrifying.
Right. The sheer violence of the initial blast is one thing, but that regional death toll, awful as it is, was eventually dwarfed by the global tragedy. Let's talk how. How does an explosion in Indonesia cause snow in New York the following June? What's the physics? Hashtag 2.1, the atmospheric mechanism. This is really the core of the deep dive, understanding this mechanism, and it boils down to two main things. How high the eruption went and what it put up there, the chemistry. Okay, how high did it go?
The Tambora eruption column was unbelievably powerful. It punched right through the normal weather layers and reached far, far higher, over 43 kilometers high.
43 kilometers? Why is that altitude so critical?
Because it gets you well into the stratosphere. See, our weather, rain, clouds, wind systems, that mostly happens down here in the troposphere.
Okay.
If volcanic ash or gas only reaches the troposphere, it gets washed out pretty quickly by rain, mixed down within days or weeks usually.
Right.
But the stratosphere, which starts around, say, 10 to 17 kilometers up, depending on where you are, it's different. It has what scientists call a temperature inversion. Meaning, as you go higher up in the stratosphere, the temperature actually gets warmer, mostly because ozone up there absorbs solar radiation. This temperature profile creates stability. There's much less vertical mixing between the troposphere and stratosphere. There's sort of an atmospheric lid at the boundary, the tropopause.
But if an eruption is strong enough to blast material through that lid,
then that material can stay suspended up there for a very long time, years even. It's above the weather, essentially. It won't get rained out.
And the key stuff that Tambora blasted through that lid wasn't the heavy ash, right? That fell out relatively quickly.
Correct. The heavier ash particles settled out faster, though they caused immediate local problems. The real climate culprit was something much lighter. A gas. Sulfur dioxide, SO2. Sulfur dioxide.
Tambora ejected a truly staggering amount of SO2. The estimates vary a bit depending on how you measure it, but they range from maybe 10 million tons on the very low end up to possibly 120 million tons.
Whoa, that's a huge range, but even the low end sounds massive.
It's enormous. And once that SO2 gets into the stratosphere, it undergoes chemical reactions with water vapor up there.
And forms.
Tiny microscopic droplets of sulfuric acid, H2SO4. These droplets are called sulfate aerosols.
Aerosols,
And they form this vast, persistent global layer, a stratospheric sulfate aerosol veil.
So these tiny droplets floating way up high, 10, 20, 30 kilometers up,
Yeah.
they basically act like a giant mirror.
That's exactly right. They significantly increase the Earth's albedo, its reflectivity.
Reflecting sunlight back into space. Incoming shortwave solar radiation, yes. It gets reflected back before it can reach the surface and warm the planet.
And that leads directly to cooling.
Sudden, short-term global cooling, what we call a volcanic winter. Tambora was the largest natural climate-forcing event of the last couple of centuries, easily.
And the numbers show it. Global average temperatures dropped by how much?
About 0.53 degrees Celsius. That's nearly a full degree Fahrenheit, 0.95 degrees Celsius, averaged across the globe in the year following the eruption.
That might not sound like a huge number, half a degree Celsius, but averaged globally, that's a massive shock to the system, isn't it?
It's a huge shock. Climate systems operate on relatively fine margins. A sudden drop like that throws weather patterns completely out of whack.
It's fascinating, too, that this whole mechanism, sulfur aerosols in the stratosphere causing cooling, wasn't really scientifically understood until much later.
Not until the Krakatoa eruption in 1883.
Yeah.
That eruption wasn't as big as Tambora, but it happened in the age of telegraphs and global science.
And it caused those weird, colorful sunsets everyone saw.
Exactly. The brilliant sunsets from Krakatoa got scientists really investigating the atmospheric effects. But Tambora had already demonstrated the principle, extremely powerfully, 68 years earlier. Proof written in, well, global famine, as you said. Pretty much. The sheer scale of Tambora's sulfur injection was key. It was just so much more than anything else in recent memory, like Pinatubo even.
And that veil spread quickly around the globe.
Very quickly.
Yeah.
Stratospheric winds distributed those aerosols fairly evenly around the globe within weeks to months, especially blanketing the northern hemisphere. Hashtag 2.2 visual phenomena around the world.
Beyond just the cooling, this global aerosol veil created some really strange and frankly unnerving visual effects thousands of miles away, things people saw in the sky.
Yes, absolutely. In the northeastern United States, particularly in 1815 and into 1816, people reported this persistent dry fog.
Dry fog, what was that like?
Well, the descriptions are eerie. It was thick enough to significantly dim the sunlight, often giving it a reddish tint. But the strangest thing, it couldn't be dispersed by wind or rain. It just hung there.
Because it wasn't really fog down low, was it? It was the stratospheric stuff mixing down.
Exactly. It wasn't tropospheric water vapor fog. It was the optical effect of that high-altitude aerosol layer.
And the sunlight was dimmed so much, people could actually see sunspots with the naked eye.
Contemporaneous accounts confirm that, yes. Which must have been truly terrifying for people who relied on the sun and sky for everything, for agriculture, for signs.
Yeah, imagine the sky just looking wrong, persistently hazy and red for months on end. That must have caused incredible anxiety.
Undoubtedly. A huge psychological impact.
But there was also this surprisingly beautiful side effect, wasn't there? Especially seen in Europe.
Yes, the sunsets and twilights. Those fine aerosol particles scatter sunlight in very specific ways.
How so?
They tend to scatter the shorter wavelengths, blues and greens, more effectively, allowing the longer wavelengths, the reds, oranges, pinks, to dominate the view, especially when the sun is low.
So you get these incredibly vibrant, colorful sunsets.
Prolonged and brilliantly colored, yes. Often described as fiery orange or red near the horizon, shifting dramatically to purples and pinks higher up. These were seen frequently in places like London, especially between June and October of 1815.
And this wasn't just a curiosity, it actually had a cultural impact on art.
It seems very likely. Sources strongly connect these unusual dramatic skies to the paintings of the great romantic landscape artist, J.M.W. Turner.
Turner's famous fiery skies.
Exactly. It suggested that the volcanic dust, those aerosols, directly influenced his palette, leading to some of his most famous works where the skies blaze with these intense, almost unnatural oranges and reds.
That's incredible. The violence of an eruption in Indonesia, filtered through atmospheric physics, ends up inspiring a major artistic movement in London.
It just shows the unexpected reach of an event like this. It wasn't just about weather and crops. It touched culture, too. Hashtag 2.3, the climate shift and the Dalton minimum.
Okay, let's look at the hard climate data again. That 0.53 degree global cooling, it wasn't just a blip. The 1810s became the coldest decade on record for the Northern Hemisphere, right?
Yes, culminating in 1816 itself, which ranks as the second coldest year in the Northern Hemisphere going back to about 1400 AD, a truly anomalous period.
And critically, as you mentioned, Tambora didn't happen in isolation. The timing was, in a way, terrible. It hit when the climate was already kind of vulnerable.
Exactly. It occurred smack bang in the middle of the Dalton minimum.
Right. Can you just briefly explain what the Dalton minimum was?
Sure. The Dalton minimum was a period roughly from 1790 to 1830 characterized by unusually low solar activity. Fewer sunspots, less solar radiation reaching Earth. It's a natural cycle in the sun's output.
So the sun was already putting out a bit less energy.
Correct. This natural solar cycle likely caused some pre-existing global cooling on its own. Scientists estimate maybe around 0.2 degrees Celsius cooling attributable just to the solar minimum during that period.
Okay, so here's the crucial question then. How sure are we that Tambora was the main driver of the extreme cold in 1816 and not just, the final straw on top of this existing solar cooling?
That's a really important distinction to make. The Dalton minimum provided a cooler background state. Think of it as lowering the baseline temperature gradually over decades.
Okay.
But Tambora provided the sudden, sharp shock. The volcanic aerosol cooling is abrupt, it's strong, and its biggest impact lasts for maybe 2 to 3 years right after the eruption.
So the rate of cooling is key.
Absolutely. That sudden drop of over half a degree Celsius globally right after 1815 simply cannot be explained by the slow, gradual effect of the solar minimum alone. Tambora delivered the massive, rapid forcing that destabilized weather patterns worldwide almost overnight.
And that shock, that destabilization, it didn't just last for one bad summer.
No, the impacts lingered. The surface temperature anomalies, especially for summer temperatures in the Northern Hemisphere, remained significantly below average for 1816, 1817, and 1818. It marked a profound, multi-year disruption that just crippled agriculture. Which brings us directly to the most famous consequence. The year without a summer, 1816? That's right. The immediate result of that stratospheric aerosol veil was this complete breakdown of normal weather patterns across the Northern Hemisphere, and the human suffering it caused was just monumental, stretching across continents.
Let's start in North America, New England, Atlantic Canada. The climate shock there seems to have been incredibly direct and devastating, especially for farmers. Hashtag 3.1 North American hardship.
It essentially annihilated the growing season in many areas.
We're talking serious cold, persisting deep into the months that should have been warm.
Extreme cold, long past the usual last frost dates. In early June of 1816, there were damaging frosts reported in the higher elevations of New Hampshire, Maine, Vermont, northern New York.
Killing off crops that had just been planted?
Completely wiped out the first plantings. And then it got even worse, much worse than just a cold night.
Snow.
On June 6th, snow actually fell in places like Albany, New York, and Dennisville, Maine.
Snow in June. It's hard to fathom.
And if you were up in Cabot, Vermont, on June 8th, historical records say the snow on the ground was still 46 centimeters deep.
18 inches in June.
18 inches of snow, and crops should have been well underway. Canada got hit hard, too. Near Quebec City, 30 centimeters, about a foot of snow accumulated between June 6th and 10th.
So for farmers, say, in Massachusetts or New Hampshire, the summer was just impossibly short.
Brutally short and cold. The effective growing season in some areas was slashed to less than 80 days. Widespread harvest failures, catastrophic failures. Most agricultural crops were simply ruined. People had to resort to eating things they normally wouldn't, wild roots, pigeons, apparently even boiled nettles.
And the impact wasn't just that one bad harvest, was it? It had knock-on effects.
Absolutely. The feed shortages were severe. During the following winter, 1816 into 17, huge numbers of livestock died in New England because farmers simply had no fodder for them.
And the winter itself was extreme, too.
Temperatures in parts of central and northern New York reportedly dropped below minus 34 degrees Celsius. That's minus 30 Fahrenheit. cold enough to freeze lakes and rivers solid, cutting off transport routes they normally relied on.
The whole food system was just crippled.
Crippled by this relentless, unnatural cold. It triggered a significant migration wave. Many New England farm families just gave up, abandoned their failed farms and headed west, hoping for better land and warmer climates.
A demographic shift literally caused by a volcano half a world away. It really was. But while North America dealt with cold and migration, Europe faced something even worse: widespread famine and social upheaval. It really was. But while North America dealt with cold and migration, Europe faced something even worse. Hashtag 3.2 European famine and social unrest.
Yeah, the situation in Europe sounds equally dire, maybe even more so. Europe was already fragile, right? Just coming out of the Napoleonic Wars.
Yes, many regions were already dealing with poverty, disruption, food insecurity. The climate shock of 1816 hit this vulnerable population and pushed the continent into what's often called the worst famine of the 19th century.
What were the specific weather effects in Europe? Was it just cold?
It was a combination. Cool temperatures, yes, but also unusually heavy rains across much of the continent. Some areas saw up to 80% more rainfall than normal during the summer.
Which is terrible for crops.
Disastrous, especially for the vital grain crops. Widespread failures across the British Isles, France, Germany, Switzerland, Central Europe.
And the human cost was immediate. Immediate and brutal. Food prices shot up, doubled, tripled in some places almost overnight. This instantly pushed the urban poor, who relied on buying food daily, into starvation.
Leading to unrest.
Profound social unrest. Desperate people took desperate measures. We see widespread food riots, the famous bread riots breaking out.
Where people attacked bakeries, grain markets.
Exactly. Demonstrations turned violent. There was arson, looting, attacks on mills where grain was stored, attacks on convoys trying to transport food. This happened in many European cities across Germany, Italy, France.
And how did governments respond? Could they cope?
Caution? They couldn't, or didn't effectively. Responses were slow, insufficient. Some authorities were accused of hoarding grain or were simply overwhelmed by the scale of the crisis hitting multiple countries simultaneously. It was hard to mobilize supplies fast enough.
The displacement sounds heartbreaking, too. You mentioned Wales.
Yes, reports describe families in Wales, their harvest totally failed, having to travel long distances as refugees, literally begging for food to survive.
And Ireland. It was hit hard, too.
Famine was particularly severe in parts of Ireland. The failure of the wheat, oat, and potato harvests there was devastating. A grim foreshadowing of the even greater famine later in the century.
And the weird weather just kept coming. Ice dams in Switzerland in the summer.
Yeah, the combination of high precipitation and cold meant that some meltwater rivers froze up again. Sources specifically mention an ice dam forming in the Swiss Alps during the summers of both 1816 and 1817.
Which is how 1816 really earned that name, Year Without a Summer.
Literally. Although it's worth noting the variability. While Western and Central Europe froze and flooded, Russia, interestingly, seems to have experienced unusually warm and dry summers around this time, starting in 1850 and continuing, which shows the climate forcing didn't just cause uniform cooling everywhere, it caused massive shifts and disruptions in regional weather patterns, extremes of different kinds. Hashtag tag 3.3 Asia disruption and disease.
It's so important we connect this globally. The crisis wasn't confined to Europe and North America. We need to bring Asia into the picture. It suffered different but equally devastating consequences.
Crucially, yes. The cooling effect, particularly in the northern hemisphere, had major knock-on effects on tropical weather systems, especially the vital monsoon systems.
The Indian monsoons, so critical for agriculture there.
Absolutely critical. The volcanic forcing seems to have significantly disrupted the timing and intensity of the Indian monsoons,
leading to
directly to 3 consecutive failed harvests and widespread famine, particularly severe in the Bengal region of India. Agriculture there was and is completely reliant on the predictability of those seasonal rains. That predictability just vanished.
And this environmental chaos, the famine conditions, it didn't just cause starvation, it also set the stage for a massive health crisis.
Yes, this is one of the most chilling and far-reaching consequences. The climate disruption in India is directly linked to the emergence and subsequent global spread of a new, particularly virulent strain of cholera.
Cholera, originating in Bengal in 1816.
That's the link scientists and historians make. The conditions created by the climate change, the failed rains followed by flooding, the changes in water levels and temperature, the famine weakening the population created ideal conditions for the cholera bacterium, Vibrio cholerae, to mutate or thrive and spread rapidly through contaminated water sources across Bengal. So, a direct line. Volcano, climate change, famine, epidemic, disease. It appears so. A truly terrifying cascade effect.
And the disruption didn't stop in India, did it? China was affected too.
Yes, the alterations to the monsoon patterns also caused severe flooding along the Yangtze River Valley in China.
Forcing people to flee.
Thousands were forced to abandon their homes and ruined farms in coastal and riverside areas due to the floods. More displacement, more misery.
And the health problems echoed back towards Europe as well. Typhus.
Yes, the general climate anomaly across Eurasia. The widespread cold, damp conditions, the mass movements of starving, weakened people is blamed for worsening and spreading typhus epidemics. These ravaged parts of southeastern Europe and the eastern Mediterranean between 1816 and 1819 is just layer upon layer. One explosion triggers this domino effect. Climate chaos, crop failure, starvation, forced migration, and major disease outbreaks across 3 continents. The scale of the indirect devastation is truly staggering. It's hard to think of another single, localized natural event in recorded history that had such a broad, simultaneous, and long-lasting negative impacts on human societies across the globe.
It really stands as the definitive historical example, doesn't it? How geology can drive global socioeconomic and public health crises.
Absolutely. A stark lesson from the past. Hashtag check outro.
So our deep dive today, it's taken us on this incredible, if grim, journey. Started with a 4,300-meter volcano in Indonesia.
And ended with snow in June in New York.
Bread riots in Europe.
And the emergence of a global cholera pandemic in India.
We have to come back to those numbers. That estimated 71,000 regional deaths near Tambora itself.
And then the estimated 90,000 additional global deaths, mostly linked to the cold, the famine, the disease.
All an indirect consequence of that single tropical eruption thousands of miles away.
That figure alone just speaks volumes about how vulnerable global systems were, even then, to sudden climate shocks. But what also makes Tambora stand out is just how long the impact lasted.
Right. It wasn't just one bad year.
No. The really weird atmospheric conditions, the direct effects of the aerosols, persisted for the better part of 2.5 years, causing havoc in multiple consecutive growing seasons.
And the actual cooling effect on the climate system lingered even longer than that initial aerosol veil, didn't it?
It did. The way the stratosphere absorbed heat and then slowly rebalanced led to a delayed surface cooling effect that actually persisted for about 9 years, right up until around 1824.
9 years of subtle but significant impact. The 1810s really were a volcanically disturbed decade. They absolutely were. And we know this with incredible certainty now, thanks to science that wasn't available back then. Ice cores. Drilled from Greenland and Antarctica. What do they show?
They provide a frozen atmospheric record. Scientists can analyze the layers of ice for trapped volcanic aerosols, particularly sulfates.
And Tambora left a clear signature.
The clearest, most dramatic signature in the record. The data is unambiguous. The Tambora eruption caused the largest spike in sulfate concentrations found in ice cores going back at least 5,000 years.
5,000 years. Bigger than anything else in that huge time frame.
By far. You see this massive spike in sulfate appearing in the ice layers corresponding to early 1816, and then it gradually tails off over the next few years. The amount of sulfur ejected is estimated from this data to be around 25 to 30 teragrams.
How does that compare to, say, Pinatubo again?
It's roughly 10 to 15 times the amount of sulfur ejected by Pinatubo in 1991. Just a different league entirely.
It's such a powerful, chilling reminder that our climate system can be dramatically forced into chaos by natural events.
Especially when, as was the case back then with the Dalton minimum, the system might already have existing vulnerabilities.
Yeah, that's a key point. Tambora didn't create those famines out of thin air. It massively accelerated and exacerbated problems that were already there. Regional poverty, the stresses from the recent wars, maybe existing localized droughts.
It pushed vulnerable systems over the edge. Which brings us, I think, to the final, really provocative thought to leave our listeners with.
Okay. Think about it. Back in the early 19th century, a time when food systems were mostly local, global population was much smaller, and the planet was actually in a natural cool phase. Even then, this single eruption caused the worst famine of the century, killed tens, maybe hundreds of thousands, indirectly worldwide.
So, now consider today. What if a VEI-7 eruption, a Tambora-scale event, were to happen now? In our current world, with ongoing anthropogenic global warming, with our incredibly complex and interconnected global supply chains, our reliance on monoculture farming, billions more people.
What level of disruption or even collapse could that sudden, forced climate shift trigger in our modern society?
It's a sobering question. The Tambora story really underscores this profound vulnerability. It shows that even in our hyper-connected, technologically advanced world, a massive geological event on one remote island could still potentially bring the entire planet to its knees.
A lesson from 1815 that feels incredibly relevant today. Thank you for joining us for this deep dive.
Welcome back to the Deep Dive. Today we're tackling a story you probably think you know, but maybe not the whole picture. It's a plot that failed spectacularly.
Oh, spectacularly is the word.
And it really did define an era, didn't it? It even gave us a holiday, bonfire night, still celebrated with fireworks and, well, fire across the UK. We are talking, of course, about the 1605 Gunpowder plot.
Yeah, and this deep dive, it isn't just about, Guy Fawkes guarding some barrels. This was meant to be a complete political reset. Annihilation, really.
You mean wiping the slate clean?
Completely. The plotters, this group led by Robert Catesby, they were aiming for the total destruction of the English government. We're talking King James I, his immediate family, the Privy Council, all the judges, most of the Protestant aristocracy, the bishops and the House of Lords, basically everyone in power gone in one big bang.
Wow. That's audacious doesn't quite cover it. It sounds like pure desperation.
It absolutely was.
And that's really our mission today, isn't it? To get under the skin of that desperate religious climate that could possibly fuel such violence.
Right. And also to look at the, frankly, almost unbelievable scope of their plan, the logistics, or maybe the lack of them sometimes.
And, of course, the famous betrayal that brought it all crashing down. Plus, the aftermath of brutal justice and the legacy that stretches right up to today.
It's quite a story.
So, to understand why anyone would even think of doing this, we really have to start with the context, the sort of historical tinderbox of early 17th century England.
Exactly. You've got the fallout from the English Reformation, Queen Elizabeth I's long reign, her religious settlement, and the result was that English Catholics were pushed to the margins. Really squeezed.
They were living under constant grinding pressure, weren't they? It wasn't strictly illegal to be Catholic, but practicing the faith openly, it was another story.
Almost impossible. And the state had tools, particularly economic ones, to force people into line. We're talking about really severe penalties for something called recusancy.
That's refusing to go to the official Anglican church services, right?
Yeah, that's it. And the fines. People hear about fines, but the sheer weight of them was designed to be crushing.
Can you give us a sense of that? What did it actually cost a Catholic family back then?
Well, for the wealthy Catholics, the fine was £20 a month. Now, you have to understand, £20 a year was a decent income for, say, a successful craftsman back then.
So £20 a month is astronomical.
Astronomical. It was ruinous. The state was pulling in something like £5,000 a year just from these fines. It wasn't just a tax, it felt like, and was intended as slow-motion economic destruction, forced conversion, or at least submission.
And then James I comes to the throne in 1603, and there must have been this glimmer of hope for Catholics.
Oh, definitely. A huge wave of hope, actually, because his mother was Mary, Queen of Scots.
A Catholic icon, really, a martyr in their eyes.
Precisely. So they thought maybe, just maybe, things would ease up. A bit more tolerance, perhaps.
But James was, well, he was a pragmatist, wasn't he? King of a largely Protestant nation.
He was. And that window of hope, it slammed shut pretty fast. By February 1604, just over a year into his reign, he publicly denounced the Catholic Church. He ordered all priests out of the country.
Wow.
And then, the real kicker for many Catholics, he brought back those crippling recusancy fines. Queen Elizabeth had actually let them lapse a bit towards the end of her life, but James reimposed them with full force.
So that hope wasn't just disappointed, it was actively betrayed from their perspective.
Absolutely. And the final nail in the coffin, it seems, according to the sources, was a speech James gave in March 1604.
What did he say?
He made it crystal clear. Catholics were, and I quote, not to increase their number and strength in this kingdom. That was it. For some priests, for the more militant Catholics, this felt like a total rejection of any earlier hints of tolerance. It signaled that the persecution, political and financial, was only going to get worse.
And that's what pushes people like Robert Catesby over the edge.
It seems so. Catesby, he'd already been involved in failed plots, like the Essex Rebellion. He'd even tried appealing to Spain for an invasion. This speech, it seems, convinced him and others like him that only something truly drastic, truly violent could work.
Which leads us to Catesby himself, the architect of this whole thing. The sources paint quite a picture, tall, imposing, from an ancient, historic, and distinguished lineage. Sounds almost romantic in a dark way.
He definitely had charisma. He was the spark, the motivator. But he was also, someone already known to the government. He'd been wounded and captured during the Essex Rebellion just 4 years earlier. So he was marked as an agitator.
Driven by faith, but maybe not the best planner.
Exactly. He could inspire loyalty, fierce loyalty, but blowing up Parliament, that required a different skill set. He was fundamentally an amateur conspirator in that sense.
So he needed a team. He starts recruiting Thomas Wintour, John Wright.
Mm-hmm.
They swear this oath of secrecy in May 1604.
Right. And get this, they actually took Mass together shortly after swearing the oath. Though the priest involved, Father John Gerard, apparently had no idea what they were planning. He was just doing his duties nearby.
Incredible. And then they bring in the man everyone remembers, the specialist.
Guy Fawkes. Guido Fawkes, as he sometimes styled himself. He's the muscle, the technician.
A bomb guy.
The bomb guy, exactly. He was recruited very deliberately because of his military background. He'd spent about 10 years fighting for the Spanish in the Netherlands. So he knew about gunpowder, sieges, demolitions, all the practical stuff Catesby lacked. He even used an alias, didn't he?
John Johnson, apparently. Which raises the question for me. If this was, potentially a suicide mission designed to cause maximum chaos, why bother with an alias at that stage?
That's a great point. I think it shows the sort of split personality of the plot. Fawkes, the soldier, he's thinking tactically. Cover your tracks, light the fuse, get away if possible, maybe escape the country. That's his training.
But Catesby?
Catesby, the ideologue, he was thinking bigger picture, beyond the blast. He wasn't necessarily planning his own escape. He was planning what came next. A whole new government.
And that's where the plan goes from just destructive to, well, almost fantasy territory. They had a succession plan.
Oh, absolutely. It's kind of mind-boggling when you think about it. So step 1. Blow up the House of Lords on November 5th during the state opening. Kill the king, his sons, everyone important.
Okay. Standard regicide plot so far.
Yeah.
Call it standard.
Right. But step 2, immediately after the explosion, a group of them would ride like mad to the Midlands. Why the Midlands? Because James's 9-year-old daughter, Princess Elizabeth, was staying there.
Ah, so kidnap the princess.
Kidnap the princess, install her as a figurehead Catholic queen. A titular queen, really.
And they even had someone in mind to run things. A regent?
They did. The 9th Earl of Northumberland.
Okay. Was he in on it?
Not a clue. That's the truly bizarre part. They planned to make him regent, but apparently never told him.
That seems optimistic.
It shows the flaw, doesn't it? You've got Fawkes's military precision, sort of, mixed with Catesby's incredibly naive political thinking. They genuinely seem to believe they could just impose a Catholic regime on a country reeling from, well, what would have been essentially a small WMD going off in the heart of its capital.
But first, they had to get the bomb in place.
And the story usually goes, they tried digging a tunnel.
They did try, but apparently they weren't very good miners. Found it really hard going, dealing with the dirt, the foundations.
Yeah.
It wasn't working out well.
So plan B.
Plan B was, well, luck seemed to smile on them, or so they thought. In early 1605, a cellar, or rather an undercroft, directly beneath the House of Lords chamber became available to rent.
Right, they just rented it.
They just rented it. It was perfect.
For-
Unused ground floor space right under the target. So they abandoned the tunnel and just started moving in the gunpowder.
How much did they get in there? 36 barrels. The sources are clear on that. And contemporary accounts and even modern reconstructions confirm it was more than enough. Enough to reduce the House of Lords to rubble, is how one source puts it.
Enough? Did they know how much was enough?
Fawkes certainly seemed to. Later analysis suggested he'd actually packed in about double the amount needed for total destruction. He wasn't taking any chances. He was a professional, remember?
Okay, so the stage is set. The gunpowder is in place. November 5th is approaching. But then a problem arises from within their own ranks.
Yeah, the human element. Despite the radical nature of the plot, some of the conspirators started getting cold feet. Not about the king, perhaps, but about killing fellow Catholics.
Because some Catholic lords would be there for the state opening, too.
Exactly. Lords Monteagle, Mordaunt, maybe others, they'd be wiped out along with the Protestants. This moral dilemma, this internal conflict, that's what led to the fatal mistake.
The warning letter.
The warning letter. On October 26th, Lord Monteagle, who was indeed a Catholic peer and would have been in the House of Lords, received this anonymous letter.
The Monteagle letter. It's famous, but what did it actually say? Was it specific?
Surprisingly vague, actually, yet deeply unsettling. The key line warned him to stay away from Parliament, saying, "They shall receive a terrible blow, this Parliament, and yet they shall not see who hurts them."
Chilling. And Monteagle didn't just ignore it.
No way. He was understandably terrified. He took it straight to Robert Cecil, the Earl of Salisbury, who was effectively the king's chief minister.
So Cecil knew first. When did the king find out?
Cecil showed it to James first around November 1st. And James had this sort of visceral reaction based on his own family history.
Right, his father,
Yeah.
Lord Darnley, killed in an explosion years before in Scotland.
Exactly. So when James read the word blow in the letter, he didn't think metaphorically. He immediately suspected, as he put it, some stratagem of fire and powder. That specific phrase, blow, perhaps triggered that memory.
Incredible intuition. Or maybe just deep-seated trauma.
Probably a bit of both. But it meant he took the threat very seriously. He ordered a search.
And the first search didn't find anything.
Not initially, or not conclusively, but on the evening of November 4th, the night before the opening, they went back for a more thorough look at the cellars and undercrofts. This search was led by Thomas Knivet.
And that's when they found him.
That's when they found John Johnson, Guy Fawkes, standing guard over the barrels. And the details of how they found him are amazing.
Oh, so?
He was fully dressed, not like someone hiding, but someone ready. He had on a cloak and hat, boots and spurs presumably, for a quick getaway on horseback after lighting the fuse.
Spurs. Ready to ride off after triggering Armageddon.
And he was carrying a lantern, which you can still see today. It's in the Ashmolean Museum in Oxford, and a pocket watch, presumably to time the fuse just right.
Caught red-handed. What did he do? Did he resist?
Not physically, no, but he was defiant. When they arrested him, he immediately admitted what he was planning to do: blow up the king and Parliament. James I himself later remarked on Fawkes's Roman resolution, meaning his steadfastness, his lack of repentance, even when captured.
So Fawkes is caught. What happens to the others? Catesby and the rest?
They got word pretty quickly that the plot was uncovered. Fawkes didn't talk initially, but his capture was enough. They knew the game was up. So they fled London, heading northwest towards the Midlands.
Back to the Plan B location, where they were supposed to kidnap Princess Elizabeth.
That seems to have been the desperate hope. They gathered horses, some provided by another conspirator, Sir Everard Digby, who had arranged a sort of fake hunting party as cover, but their escape just fell apart.
How?
It turned into a bit of a shambles. They rode hard through terrible weather, reached Holbitch House in Staffordshire, utterly exhausted, soaked to the skin and panicked. And then comes this moment of almost unbelievable irony.
Go on.
Their gunpowder, the spare powder they had with them, had gotten wet during the escape. So in their infinite wisdom, they decided the best way to dry it out was to spread it on the floor, near the fireplace in the main hall.
Oh, no. Please tell me they didn't.
They did. And inevitably, a stray spark from the fire landed on the powder. Whoosh! A flash fire. It didn't blow the house up, but it severely burned several of them, including Catesby himself.
Hoist by their own petard. Most literally. An accidental self-inflicted wound using the very substance of their plot.
You couldn't make it up. Injured, trapped, demoralized. It was over. The sheriff of Worcestershire and a posse of about 200 men caught up with them shortly after.
And it came to a fight.
A brief, desperate firefight. Catesby, Thomas Percy, John Wright, and his brother Christopher, they were shot and killed. The others were rounded up and arrested.
So the plotters are dead or captured. Fawkes is in the tower. What comes next? The investigation.
Yes, and it was led by Sir Edward Coke, a formidable legal mind. The state needed answers. They needed names, any other conspirators, but more importantly, they needed to frame this narrative.
Frame it how?
To justify what came next, particularly against the wider Catholic community. And they needed confessions, which meant torture.
Even though it was technically illegal under English common law.
Technically.
Oh.
But the king could authorize it in cases of treason, and James I did. He gave specific instructions, actually.
Oh, were they?
He wrote that they should start with gentler tortures, milder forms, and then proceed by steps extended to the bottom depths. The Latin phrase used was et sic per gradus ad ima tenitur, and so by degrees extend to the depths.
Grim. Did it work? On Fawkes?
It seems so. The physical evidence is stark. If you look at Fawkes's signature on his initial statements, it's clear. Maybe a bit shaky, but legible. His signature on his final confession, after days of interrogation, likely including the rack, it's a wreck, barely a scrawl. It shows the physical toll, that Roman resolution broken.
But the investigation wasn't just about the men caught with the gunpowder or at Holbitch House, was it? The government wanted to link it higher up.
Absolutely. They desperately wanted to implicate the Catholic clergy, specifically the Jesuits, who were viewed with intense suspicion by the Protestant establishment. This is where Father Henry Garnet comes in.
A Jesuit priest. What was his alleged role?
Garnet was the superior of the Jesuits in England. He was accused and eventually convicted of treason, specifically of misprision of treason, meaning he knew about the plot but didn't report it.
But he had a defense, didn't he? A very specific one.
He did. It raised this huge moral and legal question. Garnet claimed he had learned about the plot, but only through the sacrament of confession from another priest who had heard one of the conspirators confess.
The seal of the confessional.
Exactly. Under Catholic canon law, he was absolutely forbidden from revealing anything heard in confession, even a plot to commit mass murder. To do so would be a grave sin.
So he argued his religious duty prevented him from warning the authorities.
Precisely. But for the prosecution, led by Koch, this was seen differently. They latched onto a concept associated with Jesuit teaching at the time: equivocation.
Equivocation, meaning using ambiguous language.
Or mental reservation. Essentially, the accusation was that Jesuits believed it was permissible to lie, or at least mislead, under oath in certain circumstances, by meaning something different in your head to what your words outwardly suggested.
So the state basically said he knew, and his claim about the confessional is just Jesuitical trickery to cover his guilt.
That was the narrative they pushed, very successfully. It allowed them to paint Garnet, and by extension the Jesuits, as inherently untrustworthy, subversive, capable of plotting treason while hiding behind religious rules. It became known as the Jesuit treason.
Whether Garnet was truly complicit or caught in an impossible bind, the verdict was inevitable, I suppose.
Pretty much. The trials in January 1606 were swift. The surviving main conspirators, Fox, Garnet, they were all found guilty, and the sentence was the standard gruesome punishment for treason.
Hanged, drawn, and quartered.
The full horror. But Fox, even broken by torture, he had one last act of defiance.
What did he do?
As they were preparing to hang him, which was just the first part of the process, designed to leave the victim conscious for the disemboweling and quartering, he managed to jump from the gallows ladder or the platform.
He jumped. To what end?
To break his own neck. He died instantly from the fall. It meant he avoided the agony of the drawing and quartering, a final, desperate assertion of control over his own death.
Wow. The political fallout must have been immediate.
Instantaneous and harsh. Parliament rushed through the observance of 5th November Act 1605. This basically mandated an annual public day of thanksgiving for the plot's failure, church services, sermons,
And bonfires.
and bonfires. The tradition started almost immediately. People lit bonfires to celebrate the king's deliverance. Soon after, they started burning effigies of the Pope and then specifically of Guy Fawkes.
And that's where we get the term Guy, from burning effigies of Guy Fawkes.
Exactly. Over time, burning a guy led to the word guy becoming an informal term for a man, especially one oddly dressed, and eventually just any man. It's a direct linguistic link back to those bonfires.
Amazing. And the plot had cultural ripples too, didn't it? I've heard connections to Shakespeare.
Yes, absolutely. Shakespeare's Macbeth was likely written and first performed shortly after the plot, around 1606, and is steeped in the atmosphere of the time. Themes of regicide, ambition, guilt, but especially equivocation.
Ah, linking back to the Garnet trial.
Directly. There's even a specific reference to an equivocator who could swear in both the scales against either scale. It reflects that intense public interest and anxiety around the trial, the Jesuits, and the nature of truth and loyalty that the Gunpowder plot stirred up.
So we know the plot failed, but thinking about those 36 barrels, how close did they actually come? How destructive would it have been?
That's a fascinating question, and we actually have a pretty good idea thanks to a reconstruction done for an ITV program back in 2005.
What did they find?
They built a full-scale replica of the old House of Lords, building the dimensions, the materials, and they detonated the same amount of gunpowder, 36 barrels, though they had to use modern powder adjusted for likely 17th century quality.
And the result?
Utter devastation. The replica building was completely obliterated, just vaporized, basically. Experts calculated that no one within about 100 meters or 330 feet would have survived the initial blast. Windows would have been shattered across Westminster. It confirmed Fox's plan was lethally viable.
So it absolutely would have worked. A terrifying thought. It failed, but its impact, as we've discussed, is huge and lasts centuries. But the story isn't quite settled, is it? There are still lingering questions, even conspiracy theories.
Absolutely. The neat official narrative, Catholic fanatics foiled by loyal Monteagle and clever King James, that's been questioned almost since the beginning.
What's the main alternative theory?
The big one centers on Robert Cecil, the Earl of Salisbury, James's chief minister, the man who got the Monteagle letter. The persistent theory around since the 17th century is that Cecil was involved.
Involved how? That he was secretly a plotter.
Not usually that he was a plotter, but that he either knew about it far earlier than he let on and allowed it to proceed, or perhaps even helped nudge it along through informants or agents provocateurs. Some even suggest elements of the plot might have been fabricated or encouraged by the state.
But why? What would be the motive for someone like Cecil, the king's right-hand man, to let a potentially catastrophic plot run almost to completion?
Power. Politics. The theory goes that Cecil saw an opportunity. By letting the plot develop to the point where it could be dramatically revealed and stopped, he could achieve several things.
Like what?
Well, first, solidify his own position as indispensable to the king, the man who saved the realm. Second, create undeniable justification for a major crackdown on Catholics, pushing through much harsher anti-Catholic laws than might otherwise have been possible. Basically, use the plotter's extremism to discredit all Catholics and consolidate Protestant control.
So, the ultimate Machiavellian move. Letting your enemies almost succeed to give you the perfect excuse to crush them completely. A sort of early modern deep state theory.
You could certainly frame it that way. It suggests that even the spectacular act of intended violence was perhaps, in the end, managed and manipulated by the state itself to achieve its own political goals.
It certainly adds another layer of intrigue, doesn't it? It means that even now, over 400 years later, what exactly happened in that undercroft and who knew what when isn't entirely clear.
The smoke from the gunpowder and maybe from the bonfires hasn't completely cleared.
A provocative thought indeed. Something for you to think about the next time you see fireworks on November 5th. Thank you for joining us for this deep dive.
Welcome to the Deep Dive. Today we're getting into something pretty fascinating, a cosmic object that's, well, a bit of a contradiction.
That's a good way to put it.
Yeah, on one hand, it's this amazing scientific time capsule, potentially holding the secrets to life itself, pristine stuff.
Right, the raw ingredients.
But on the other hand, it's officially flagged as a potentially hazardous object, something that, could pose a real risk down the line.
Absolutely. We're talking about 1955 Bennu. It's a carbonaceous asteroid discovered back in 1999.
And it's on that Century risk table.
It is. Its orbit gets pretty close to ours, uncomfortably close sometimes. But there's more to it. Even the name has a story.
Oh, do tell.
Well, Bennu comes from Egyptian mythology. It's this bird, like a heron, linked to the sun, creation, rebirth, that sort of thing.
Okay, interesting connection.
And the name was actually suggested by a third grader, Michael Puzio. He saw the OSIRIS-REx spacecraft's sampling arm and thought it looked like the neck and head of this Bennu bird.
No kidding. A third grader. That's brilliant. Ancient myth meets space-age tech.
Exactly. And that mission, OSIRIS-REx, is really our main source for this deep dive. It was a huge undertaking.
7 years, wasn't it? Launched 2016, got there 2018.
That's right. Then that incredibly tense, brief touchdown in 2020 to grab a sample.
And the sample capsule just got back to Earth last year, September 2023. So you, listening, get the highlight reel of 7 years of exploration.
We're going to unpack what we learned about this asteroid dynamic. Dark, maybe a bit dangerous.
Let's start with what it actually looks like, its physical nature, because that seems key to everything else.
Definitely. Size-wise, it's not enormous. About 490 meters mean diameter, that's roughly 1,600 feet.
But it has that very specific shape, right? Like a spinning top.
Yeah, roughly spherical, but with this noticeable bulge, a ridge, right around its equator. Very distinctive.
But didn't initial observations get it kind of wrong?
They really did. From Earth, it looked, well, relatively smooth. Maybe a bit lumpy, but generally smooth.
And then OSIRIS-REx arrived.
And sent back these incredibly detailed images. The reality was completely different. Way, way rougher than anyone anticipated.
Oh, for how?
Covered in boulders. We're talking over 200 boulders bigger than 10 meters across. And the biggest one, a monster.
Hmm.
58 meters wide. It just dominates the landscape in some areas.
Wow. Okay, so not smooth at all. More like a giant pile of rocks. Which brings up the structure, doesn't it? How does something covered in huge, sharp rocks hold itself together, especially with that spinning top shape?
That's the million-dollar question, or maybe billion-dollar, considering the
Mm.
mission cost. The answer lies in its density, or rather its lack of
The
density.
density.
It's astonishingly low, about 1.190 grams per cubic centimeter.
Wait, water is 1 gram per cubic centimeter, so this is barely denser than water.
Barely. Which tells us it's not solid rock through and through. Not even close.
So what is it then?
It implies it's incredibly porous. What we call macroporosity is estimated at around 40%.
40%, so nearly half of its volume is just empty space, voids inside.
Exactly. Think of it as a loosely packed collection of rocks and dust, barely holding itself together with its own weak gravity. It's the classic definition of a rubble pile asteroid.
A rubble pile. Okay, so it's not one solid body, just a collection of bits.
Precisely. And this loose structure led to one of the most surprising moments of the entire mission, the sample collection itself.
Yes, the famous ball pit moment.
That comparison really stuck, didn't it? The surface regolith, the loose top layer, was just incredibly soft, unconsolidated.
How soft are we talking?
So soft that the mission team calculated the spacecraft actually punched down into the surface quite a bit during that brief contact. They said OSIRIS-REx would have sunk into Bennu had it not fired its thrusters to back away immediately.
Wow, so it didn't really land. It sort of bounced off this cosmic pillow.
Kind of, yeah, like landing in a giant pit full of plastic balls.
Yeah.
Very little resistance, which is just mind-boggling for something that size.
It really is this fragile, porous giant, and yet it's also considered potentially hazardous. That seems like another contradiction. How can something so loosely packed be a threat?
Well, its internal structure doesn't stop its orbit from bringing it near Earth, and its dynamics are really complex. That brings us to the second part, the forces acting on it.
It's not just passively orbiting, is it?
Not at all. Bennu is what we call an active asteroid. OSIRIS-REx actually observed it spitting out particles. Plumes of dust and even small rocks, up to 10 centimeters across, were seen leaving the surface.
Whoa, what causes that?
There are a couple of leading ideas. One is thermal fracturing. The temperature swings between day and night on Bennu are extreme. That constant heating and cooling can crack the surface rocks, causing bits to break off.
Makes sense, like rocks cracking in a desert on Earth, but, in space. What's the other idea?
It likely relates to the water we know is locked inside Bennu's minerals.
Right. You mentioned water earlier.
Yes, it contains hydrated minerals, things like phyllosilicates. These formed when liquid water interacted with rock on Bennu's much larger parent body billions of years ago.
So there's water ice or water molecules trapped in the rock?
Essentially, yes. And when the sun heats these minerals, the water can be released as vapor. This outgassing can act like tiny jets, pushing surface material away.
So it's cracking under the temperature swings and venting steam, basically, shedding its skin.
Pretty much. And all this heating and cooling, especially the uneven way it happens, leads directly to the biggest factor influencing its orbit long term, the Yarkovsky effect.
Right, the Yarkovsky effect. This sounds subtle, but it's crucial, isn't it? Explain how this works.
Okay, so imagine Bennu rotating. The side facing the sun heats up. As that heated side rotates into darkness, it radiates that heat back out into space as infrared light.
Like a hot pavement cooling down after sunset.
Exactly. But that radiated heat carries a tiny amount of momentum. It acts like a minuscule continuous thrust pushing the asteroid. Because the heating and cooling isn't perfectly even across the whole surface, this push isn't random. It nudges the asteroid consistently in one direction over time.
And it's tiny, but it adds up.
It adds up significantly.
Huh.
For Bennu, this effect causes its average distance from the sun, its semi-major axis, to drift by about 284 meters every single year.
284 meters a year, that's huge on an astronomical scale. That makes predicting its exact path really tricky long term.
Incredibly tricky. And there's another twist. The Yarkovsky effect is also changing its rotation speed. It's causing Bennu to spin slightly faster over time. The rotation period is decreasing by about 1 second every century.
So it's drifting and speeding up its spin. No wonder NASA wanted to study it up close. Measuring that effect precisely is vital for planetary defense, right? To predict where it and others like it will actually be.
That was a major reason for choosing Bennu, absolutely. It being potentially hazardous wasn't just a coincidence, it was part of the point. We needed to understand these subtle forces better.
So let's talk about that hazard assessment. Now that OSIRIS-REx has helped refine the orbit and the Yarkovsky measurements, how serious is the risk?
Well, the calculations show a cumulative probability of Bennu hitting Earth between the years 2178 and 2290. That cumulative chance is about 1 in 3,750.
Okay, still low odds overall, but not zero. Is there a specific date that stands out?
Yes, the single highest probability impact date is calculated to be September 24th, 2182. The chance on that specific day is about 1 in 2,700.
And if that unlikely event did happen, what kind of impact are we talking about?
The energy release would be immense, estimated at 1,200 megatons of TNT equivalent.
1,200 megatons. How does that compare to something we know?
Well, the Tunguska event in Siberia in 1908, which flattened a huge area of forest, is estimated at maybe 3 to 5 megatons. So Bennu would be hundreds of times more powerful. It's a civilization-altering scale of impact, though not an extinction-level event like the dinosaur killer.
That's sobering. But you mentioned the risk depends on something happening much sooner, right? In 2135.
That's right. In 2135, Bennu makes a close but safe flyby of Earth, passing about 203,000 kilometers away. That's closer than the Moon.
Still sounds pretty far. Why is that flyby so critical for the 2182 risk?
Because of gravity, specifically Earth's gravity. During that close approach, if Bennu passes through certain very small regions of space near Earth called gravitational keyholes, our planet's gravity will tweak its path just right.
Just right, to put it on a collision course for 2182.
Exactly. These keyholes are incredibly small zones. Some calculations suggest they could be as narrow as 5 meters wide.
5 meters, that's tiny. The width of a car determining the fate of an asteroid half a kilometer wide decades later, that really highlights the precision needed.
It absolutely does. Tiny changes now lead to huge differences later. But, looking at the really, really long-term picture might offer some perspective.
How so?
Over the next, say, 300 million years, models predict Bennu has about a 48% chance of eventually falling into the sun.
Okay, that's the most likely fate.
Then about a 26% chance of hitting Venus, and maybe a 10% chance of hitting Earth over that vast time scale.
Right.
So while the near-term risk is real and needs monitoring, we aren't its most probable final destination.
Right. Which loops us back to why we went there in the first place, not just the hazard, but the science. The chance to study this pristine, carbon-rich material.
Exactly. That was the primary scientific driver. Finding the origins of water and organic molecules in the solar system, things that could have seeded life on Earth.
And they specifically targeted the Nightingale site for the sample grab because it looked different, right? Redder.
Yeah, spectrally redder, which often suggests fresher, less space-weathered material, closer to its original state. And even before the sample came back, the instruments on OSIRIS-REx confirmed Bennu was water-rich.
Finding those hydrated minerals you mentioned, the phyllosilicates and magnetite, evidence of past liquid water.
Correct. Strong evidence that liquid water was present on Bennu's parent body, wherever that was, billions of years ago. The estimates for water content locked in minerals are around 1% by weight minimum, maybe up to over 6% potentially.
And then the sample itself arrived. How much did they get?
Way more than planned. The goal was 60 grams. They ended up with 121.6 grams, a huge success.
Double the goal. And the material itself, you said, very dark.
Extremely dark. It visually resembles those very rare CI chondrite meteorites, which are considered among the most primitive materials we have. But Bennu's sample is even more pristine, obviously, having not gone through Earth's atmosphere.
What makes it stand out from those meteorites?
Well, besides being untouched by Earth, it has a really high carbon content, around 4.5 to 4.7% by weight. And significantly, it's packed with pre-solar grains.
Pre-solar, meaning grains that formed before our sun even existed.
That's right. Tiny specks of dust forged in other, older stars that got incorporated into our solar system as it formed. Finding lots of them confirms we're looking at incredibly old, fundamentally unchanged material from the dawn of the solar system.
Wow, okay. That really sets the stage for the biggest discoveries, particularly for astrobiology. The analysis reported early this year, 2025. What did they find in that ancient carbon-rich dust?
This is where it gets truly exciting. They found phosphate minerals, which are crucial. Phosphorus is the backbone of DNA. But the real headline was the organic compounds.
We knew asteroids had organics.
We did, but the sheer diversity and completeness found in the Bennu sample was staggering. It's like they found the whole toolkit.
Okay, give us the specifics, the building blocks of life.
They identified 14 of the 20 amino acids that life on Earth uses to build proteins. 14. These are essential for constructing complex biological machinery.
14 out of 20. That's incredible.
But wait, there's more, and this might be even bigger. They found all 5 nucleobases.
All 5. You mean adenine, guanine, cytosine, thymine.
And uracil. The A, G, C, T, and U that make up the letters of the genetic code in DNA and RNA. All 5 were present in the Bennu sample.
All of them. In pristine condition, delivered from an asteroid. That's profound. It means this dangerous rubble pile basically carried the instruction manual for life as we know it.
It strongly suggests that, yes, it shows these complex molecules, the absolute fundamental precursors for biology, weren't some fluke that only happened on Earth. They formed out there in the early solar system on asteroids like Bennu or its parent body.
Amazing. So let's recap this for you, our listener. We've looked at Bennu, this dynamic, spinning, shedding rubble pile that's slowly drifting closer thanks to the Yarkovsky effect. We studied it partly because it poses a potential, albeit small, risk to Earth way down the line around 2182.
A risk defined by tiny gravitational keyholes during a 2135 flyby.
Right. But investigating that risk led to this incredible scientific payoff. A sample twice as large as expected returned from Bennu.
And that sample contained truly ancient material, rich in carbon and water.
And crucially, it held the key ingredients for life. 14 amino acids and, remarkably, all 5 nucleobases needed for DNA and RNA.
It really ties together the 2 big goals of the mission. Planetary defense, understanding the hazard and origin science, understanding where we came from. We went to study a potential threat.
And found the building blocks of our own existence.
Precisely. And that leaves us with a really provocative thought, doesn't it? Given how packed this sample is with pre-solar grains, and the fact it contains the complete set of nucleobases, what does that really tell us?
About how common these ingredients are.
Exactly. How universally distributed are these fundamental building blocks of life throughout the solar system, maybe even the galaxy? Were they essentially everywhere, just waiting for the right conditions, like those found on early Earth, to assemble? That's the deeper understanding these Bennu samples are starting to unlock.